All right, good morning. Playing games with Zoom. All right, hope everybody's doing well. Let's talk about ODPs. So, ODP 411 first. So remember the goal here was to write a function that takes a string, parses it, and returns either the value of the integer that that string represents, or returns a -1 to indicate an error condition. And this is an exercise in using scanf. So it can be as straightforward as this. Let's see. Hold on a second here. All right, this is the right one. So yeah, so your parse function takes an integer, takes a string argument. I called it arg. Does an scanf with arg as a %d, and saves the result in a variable called I. This is the critical part, and not everybody did this, and you can luck out and get away with code that works sometimes if you don't do this. You need to look at the return value from scanf. Okay, that will tell you if you found an integer or not. If your string has stuff in it that's not an integer, return will be different from 1. And that tells you something's wrong with the input, return a -1. If you don't check this value of RET, in this case the return value from scanf, you have no way of knowing if I got changed or not by the scanner, right? So you can check to see if I is between 1 and 4, but you know, if I happen to have an initial value of 2, you would think that the string converted to a 2, when in fact the string might have had gibberish in it. So you've gotta check that return value from the scan function. Okay, and like I say, if you did not do that in ODP 411, and there's about half dozen people who did not, it may still work for you. Okay, because if you only call this function once, it may be that the initial value of I is 0, and it fails this test for that reason, right? But scanf does not change the value of I if it returns something different from 1. So you got to check that return value. And so that's going to come in even more strongly in 411b. So 411b is almost exactly the same as 411, with one difference, which is we want to do more precise error handling. So we want to actually check to make sure that your input doesn't just begin with a legal integer, but is exactly a legal integer, so that things like this or this get caught and thrown out with a return of -1. All right, and scanf will make this really easy to do. So how does scanf work? All right, here's the way that we would do this in ODP 411. Take a string, try to convert it to an integer. If it succeeds, store that integer in num and return a value of 1. So if string is, a 2-character string containing a 1 followed by a 5, this will set num equal to 15, it'll set return equal to 1. And then your code goes on and does its thing. If your string is equal to 15x, exactly the same thing will happen. Because scanf starts at the beginning and it says I'm looking for an integer. Could that be part of an integer? Yeah. Could that be part of an integer? Yeah. Could that be part of an integer? No. Okay, well I'll take the first 2 characters and I'll convert those into num and I'll set return equal to 1. So scanf, when you ask it to convert something with a %d format, you're not saying the entire string from beginning to end has to be an integer. You're saying the string has to start with something that matches a %d. And so scanf with this conversion has no way of knowing whether you entered a 15 or a 15 followed by something like the letter x. Alright, so if we want to be very precise about error handling, for example, if we want to be able to pick up 2x as an error or 2.3 as an error, we need to know not only that the string started with an integer, but that it didn't have anything else after it, except maybe spaces or a new line or things like that. Alright, so there's a trick we can do. Go ahead and do your %d, but then follow it with a %s. And make yourself just a throwaway array. Temp, for example. And try to scan your string with this conversion format, a %d, which is an integer, followed by %s, which is anything other than white space, right? Anything after spaces, tabs, new lines, things like that. And store your integer in num and store your string in temp. And save the return from scanf in return. And then again, see if the return value is exactly 1. If it is, you've got a good integer. But if your string looks something like 15 followed by other stuff, that 15 will get converted with %d into num. That other stuff will get converted with %s into temp, and return would be equal to 2. And that tells you you had a problem with your string because it wasn't just an integer, it had some other stuff after it, other than white space. I would not put a space between %d and %s. Spaces are weird with scanf, right? They're more or less ignored. They separate things sometimes. So an integer space integer will scan as 2 %ds. But I would put these side by side, right? And let scanf absorb the spaces. So if you just put in a 15 or a 15 with a new line at the end, this will return 1. And it'll say, I was able to convert one thing, but not the second thing. That's when you know you had good input. Alright, so let's do some code around that. I'll write a bit of a loop. All right, so let's read a line from standard in. Let's be polite and print out a prompt. So our return value, scanf, string, %d. Let's do it the old way first. Alright, let's see how we did here. So if I say try and I type in 12, it says found an integer. It's typo o'clock. 45 found an integer. Negative 23 found an integer. 001 found an integer. Haha, invalid input. Alright, the problem with this approach is, right, if you do that, it says found an integer. So it ignores the stuff that came after the integer. All right, so let's do the more nuanced version. So let's scan with a %d followed by a %s, and then let's save that extra stuff in this variable temp. So 12 works, haha, fails. 12, haha, now it notices that's invalid input. 12 space, haha, invalid input. 2.3, invalid input. Empty line, invalid input. Negative, negative 2, invalid input. All right, so this is pretty solid. Right, integer with extra spaces at the end, no problem. Spaces in the beginning and the end, no problem. Spaces in the middle, 2 integers, invalid input. All right, let's see. Question: does scanf completely flush the buffer after it finds what it's looking for? So you're looking for an integer, but the user type 15x. Is that x waiting? So scanf. This is the whole reason that we use scanf instead of scanf. Scanf looks at the characters in this string, and it always starts from the beginning of that string. And if I call scanf once on the string and then I call it again, it's going to start from the beginning of the string again. Right? So it does not flush a buffer in some sense. It always starts from the beginning of this character array and tries to do the scan. And that's the whole advantage of using scanf with fgets instead of using scanf, because scanf keeps track of where it is, and if it absorbs some part of your input, you can't go back and rescan it a different way. All right, so scanf always starts at the beginning. All right, so something like this is what you want for ODP 411B, right? Exactly the same as 411, except try to scan an extra string and save that string in a temporary variable that you're not going to do anything with, right? And if scanf returns something other than 1, you've got a problem. If you have extra stuff, it'll return 2. If you don't have an integer in the beginning, it'll return 0. If your input is completely empty, it'll return -1. So again, don't say if return is 0, then there's an error. Say if return is not 1, there's an error, right? Or if it is 1, then there's not an error. So just do the comparison to 1. All right, that's just a little trick. There is a bit of a security issue here. Okay, using scanf, scanf with a %s is potentially unsafe. There's a risk of a buffer overrun here. All right. If you're worried about that, what do? Well, you take your string and before you do the scan, throw a null terminator at, position 98 or something of the string, far enough out that it's not a problem where it's going to interfere with the valid input. But if somebody tries to load in 16,000 characters in response to this input and try to subvert your code, you'll terminate the scan of the %s where that null terminator appears. We're not going to worry about that here. That's a different course. So yeah, just scan with a %d, %s. Don't use a %c here. %c will absorb a space or a new line, right? And if you get input from, say, fgets, right, it's always got a new line tacked on to the end, and that does not mean you did not have valid input, right? So don't use %c, use %s. Okay, this is one of these things where I'm telling you exactly what to do, but a third of the class is not here, and hopefully they're watching this later, or now if they're watching it, and pick up on that. But if you want to help your friends out, you can remind them of that. Use a %s, right? Check the return value, make sure it's equal to 1. All right, questions on that? So that's the only difference from 411 for ODP 411B. All right, questions on argc, argv, which we were talking about yesterday. Questions on the quiz. So only a few people have done the quiz, but the average quiz time is about 10 minutes. A few people did it in 1. A few people took like 13 minutes, but it's not a big time suck. Okay, it's a lab exercise. Pretty easy, unsolicited opinion. Yeah, don't forget the quiz 1. All right, so yeah, so our topic for today is this whole char star versus char buffer bracket number. So someone just asked what the char star is for, so we're going to talk about that the rest of today. All right, so let's talk about strings in C. So C, probably the thing that bothers people most, if they're bothered by C, is the way that it deals with strings. Okay, C does not have a native string type, right? We sort of trick it into doing things with strings by using arrays. So arrays are a real thing in C, right? We can say integer data bracket 10. And this lets us refer to data bracket 0, data bracket 1, etc. All right. When you declare an array in C, what you're doing is a couple of things. One, you're telling the compiler, I'm going to use the word data, D-A-T-A. It's going to refer to a bunch of integers. Okay, it's going to refer to integers that I access with data bracket some index after that. So data element 0, element 1, and so on. It finds a location in memory. Actually, it arranges for the linker to find a location in memory where an integer can be stored. And let's just suppose this is location 200. All right. So it will arrange for somewhere in memory to be set aside to store some integers. Okay. So it'll say, okay, let's store our integer starting at memory location 200. And integers take 4 bytes. So data bracket 0 will be stored from locations 200 through 203. Location 204 would be data bracket 1. Location 208 would be data bracket 2. Let's go with hex. Location 20C would be data bracket 3. Location 210 would be data bracket 4, and so on. And it arranges to set aside this block of memory, these 40 bytes, which collectively we can think of as our data array. Okay, here's the really weird part, and this is the part that's absolutely essential for understanding any of this stuff. When this is done, data is really just like an integer, a single integer, and it's initialized to the value 200. Okay, the word data does not correspond to the value of the first element in your array. The word data in the compiler's mind is the address where the array begins. All right, and that's how all arrays in C work. If you declare this to be an array, then the word data itself is an address, and it's the address where data bracket 0 is placed in memory. Okay, that's probably the one thing that you absolutely have to understand and believe to be able to do anything with arrays or pointers or anything else in C. Okay, so when we have an array, the name of that array actually refers to the address where the array begins. Now, the other thing we can do in C is we can have pointers. And if I make a declaration like this, I'm telling the compiler data is going to be something like an integer, right? It's a big integer, but I want it to hold an address, not an actual integer value. The fact that I said int here has nothing to do with what type of thing data is. Data is an address. If I say char star data, data is still an address. It's a big integer. If I say structure, big long structure with weird name, star data, data is still just an address. It's a 32 or 64-bit integer, depending on your architecture, that represents where this thing is stored in memory. All right, so that's the first dualism we have to deal with. An array and a pointer are kind of the same thing, right? For different reasons, they each point to some location in memory. This could be pointing to an integer for any reason. It could be something that I use malloc for, if you remember malloc from 121. It could be something that I set up myself because I'm trying to hack the system, right? But for some reason or another, data is the address of an integer. All right. But up here, when I say integer data bracket 10, a lot more is happening. I'm asking the compiler and the linker to find a spot with enough memory to store 10 integers, set that aside so nothing else will try to use it, and then set data equal to the address of that first integer. All right, so all that stuff happens when you do this. Here, all I'm doing is saying data is going to point to an integer. I'm not saying what value it has right now. I'm not saying what location it points to right now. And I'm not doing anything with those locations. I'm not even guaranteeing that there is somewhere in the memory to store an integer or a bunch of integers. All right, so when I write my C code and I want an array, I usually do this. But once everything is compiled and running, it's as if I did that. It's just that data has been initialized to some location in memory. Okay, so here's one of the other things about C. Arrays don't come with a predefined length. If I declare data to be an array of 10 integers, once my code is running, there's nothing in there that says data can only hold 10 integers. Now you put different switches on your compiler, you can add things that will check if you go out of bounds and so on. But by itself, right, there's nothing about this variable data that I can do to get back to this number 10, to know, hey, I'm only allowed to store 10 things in here. There's no inherent length to arrays in C. So I might declare this to be an array of 10 integers, but if I try to store 11 things in there, the code will let me do that. Okay, it will let me do that until something in the memory subsystem steps in and says, you're trying to use a memory location that you're not allowed to use. And then you get something like a seg fault. But this length of an array is a programmer notion, and it doesn't really map to anything in the machine code. Okay, for this reason, we have a trick that we use when we use character arrays. Because character arrays, we definitely care how many characters we have, because these are strings. So we add a special value at the end of our array. That's what the null terminator is. So if I want to store the string hello, H-E-L-L-O, I do it like this. I store the ASCII code for H, E-L-L-O, and then in the next position, I store an ASCII code of 0. It's a null terminator. And the understanding is any string that I write is not going to contain a null terminator by my intent. Right? I wouldn't want to use a period here because I might want a period in the middle of my string. I wouldn't want to use a space because I might want a space in the middle of my string. So we pick a code that's not going to appear in my string normally. That's a null terminator, ASCII code 0. And we have this convention that if you start reading the characters in a string, character array, when you get to a null terminator, that's the end of the string. But it's just a convention. But it's a convention that's understood and followed by printf and scanf and fgets and string length and string copy and string compare and all these other string manipulating functions. All right, we don't have something like a null terminator for integer arrays. Because what integer could we use to say this marks the end of the array? Well, we can't use 0 because I might want 0 in my integer array. I can't use -999 because that might be a number in my integer array. There's no number we can use to say, okay, this marks the end of my array in general. Now, if I'm inputting scores, I could use a -1 and say when you have a -1, that's the end of the array, because I don't expect a negative score. But in general, there's nothing we can do that's analogous to a null terminator for strings. So this is a challenge, and it's a big source of seg faults and other problems that we just have to live with, right, until we get to Java and Spring. And then we've got genuine strings and arrays and stuff. All right, so back to character arrays now. We have two things that we see when we look at code. All right, we'll see char star str and char str bracket some number. All right, same thing that happened with our integer arrays. This is saying I want somewhere in memory that can hold 120 characters, and I want str to be the address of that first character. This is simply saying str is going to point to a character. So in our code, when we prototype, we say this argument should be a char star. All right. We don't know how big of an array we want to pass to our parse function. If we knew we always wanted to pass 16 characters, we could say this is a char bracket 16, right? But what if someone wants to pass 20 characters? So we declare this to be a char star. And when we write the function itself, we're going to say char star something, you know, some variable name. So let's write a function that does some sort of string processing. So I'm going to prototype it up here. It's just called process. Let's return an integer. And let's call fgets. And let's pass our string to process. All right, and let me go ahead and write a process function right here. And what should our process function do? Let's just find the length of the string. Okay. All right, so here's a short program for looking at a string, which we're calling arg, and let's just loop through and see if arg bracket I is different from 0. If it is, let's keep going. Okay, when we get to an element where arg bracket I is equal to 0, we will exit this loop, and then let's just return I. All right, so I'm going to put in a string hello, and it'll tell me process returned 6. Okay, if I just hit an enter, it tells me process returned 1. And remember, fget puts a new line on the end. So if I put in an empty line, my string that I'm passing to my process actually has 1 character in it. That's the new line. All right, so I'm not too worried about the mechanics of how this thing is counting. I just want to look at the passing of strings back and forth. Okay, so let's get rid of temp and let's get rid of num. All right, so what's going on here? str contains space for 120 characters. I need that space because I'm going to pass this to fgets, and I'm going to ask fgets to read from my keyboard, that's standard in, and store the characters it reads into memory starting at location str. And I'm telling fgets you have 120 characters worth of space. Okay, that's why I declared my array up here to say I want space for 120 characters. And I passed that string just by its name to process. Process, I can look at the other way of representing a string, which is it's a pointer to a character. And I don't know how big it's going to be. If I knew it was going to be 120 characters, I could say this is a character size 120 array. But I don't know how big it's going to be. So I just say, you know, my argument to this function is a pointer to a character. But that's the same thing as an array. And I can say argument bracket some index, And, you know, arg bracket 2 will be the same as str bracket 2. Why? Because arg and str are both the same value, which means they're both pointing to the same location in memory, which is where my character array is stored. So this does make sense, but it takes a while sometimes for it to make sense. And it doesn't necessarily need to make sense perfectly for you to be able to use these constructs. Okay. The important thing is, in my main program in this case, I'm actually setting aside locations in memory to store characters. I've got to say, give me space for, say, 120 characters. In my function, my understanding is that the thing that's passed to my function will be a string. It will be the address of a chunk of memory. So I don't need to specify to the compiler that I want to set aside space for this argument. That space will already have been set aside by whoever is calling this function. So down here, I'm fine to just say char star arg. Okay, so what are some of the variations on this that will segfault? Suppose I do this. Char star str. Right? So I run try3, I type in hello, I get a segmentation fault. Why is that? Because right here, I'm calling fgets, which says read from my keyboard, up to 120 characters and store in memory starting at location str. Well, I did not ask the compiler to set str to point to a block of memory that can hold 120 characters. And so str has effectively a random value. It's pointing to a random spot in memory, which is most likely not even a valid memory location. And fget starts trying to store what I typed in at that location in memory. It gets a seg fault. All right, so if you really need space to store something, you've got to ask the compiler to set that aside for you. And we usually do that by saying char str bracket 120. Now, since we're here, I'll mention this, but we're not going to really get into this until CSE222. But this is the other thing that you may have seen. This says str is a pointer to a character. Okay? But it's not pointing anywhere in particular yet. It's uninitialized. But what it can do is this. I can say I want to allocate 120 bytes of memory somewhere, and I want str to point to that. And you need standard lib to be able to use malloc. Right, so if I do that, everything works great. Without that malloc, right, you can get a seg fault. So malloc is just a different way of allocating memory space for a string, but the usual way we do it is by declaring it to be an array. Alright, questions about this so far? I plan to play with it a little more. So what if I tell the compiler I only want 2 bytes available for this array? Well, if I put my string in as hi, it tells me I had 3 bytes in my string. That's okay. If I say hello, it tells me I had 6 bytes in my input. That's okay, right? I seem to be getting away with something. I told the compiler I only want 2 bytes available for string, but I entered in 5 or 6 bytes, and I didn't get a seg fault. All right, there's some wiggle room, and that's kind of unfortunate, because that means you might have a problem in your code and not notice it right away. Right? If I meant for this to be 200 and I accidentally did 2, and this is all the testing I do, I'm like, yeah, my code's good, and I turn it in, or I pass it on to whoever's going to use it, and so on. And then if somebody types something longer, well, now we got a different response, right? So this is where things get interesting, right? So this is a buffer overrun, but normally when you compile code in C, there's extra stuff put into your code to detect if you go outside the bounds of an array, right? So in C itself, there's no notion of how long an array is, but in practice, with a modern C compiler, when code is compiled, there's extra stuff put into memory somewhere past the end of your array. There's things called canaries. And the canary is there to know if something happened that went beyond the end of your array. Okay, it's not very precise. You can get a little bit beyond the size of your array and be okay. But if you go too far past, the system will detect that. And so there's extra code compiled into your executable program to detect when you basically go outside the bounds of an array. And you can turn that on or off with different flags on your GCC command. By default, it's turned on, and you get a message about what's called stack smashing. All right, so let's take a little more look at this. So I'm going to declare str to be an array of 120 characters. All right, and let's get rid of this malloc business. And maybe I'll leave it in there for now. Let's just play with str. So I'm going to get rid of all of this stuff. I'm going to declare str to be an array of 120 characters, and I'm going to say, let's print out the value of str as an integer, because I've been telling you str is kind of like an integer anyway. And let's just see what that does. And it'll give me some warnings. I'm going to ignore them. And if I print this out, str is negative 1113735,120. It's some weird number. And if I run it again, str is some other weird number. And every time I run this, I get a different value. All right, let's print this as a %p. %p is a way that we can print the value of a pointer. It will print out in hexadecimal, and it will be either 32 or 64 bits, depending on the architecture that we're running on. I'm pretty sure this server is a 32-bit virtual machine, so I think it'll be a 32-bit integer. Nope, it's 64. All right, so there's the value of str, and it varies from run to run. But it starts with a 7FFF. 7FFF is a bunch of ones, okay? And this is a value on the stack. We'll talk about stacks in 222. We talk about stacks in 270 if you've already done that course. But this is a memory location, okay? This is the spot in memory where these 120 characters would be stored. So yeah, that's the value. That value is the address of str bracket 0. And we can see that for sure. Let's just print out the address of str bracket 0. And while we're here, let's print out the address of str bracket 1. And while we're here, let's just print out the address of str bracket 2 just for fun. All right, so str itself is this location in memory. That's also the address of string bracket 0. This is the address of string bracket 1. This is the address of string bracket 2. The elements of the array str are stored at consecutive locations in memory. Just for fun, let's make this an array of integers. Well, now str has this address which ends with 5d0. That's the address of str bracket 0. Str bracket 1 is at address 5d4. Str bracket 2 is at address 5d8. Those addresses are separated by 4 because integers take 4 bytes in memory. So wherever the first element is stored, the next element is 4 bytes later, the next element is 4 bytes later. And the main point here is that this str, the name of the array, is actually the address of the first element. Okay? It's different from str bracket 0 itself. Right? If we actually print out not the address of, but the actual element, str bracket 0, bracket 1, bracket 2, we get different things, right? We get random stuff because we haven't initialized the contents of the array. When we declared str to be an integer array, that initializes the value of str, the location in memory where the array is stored. So str gives us a reasonable value. But the contents of the array, we haven't initialized those. We didn't say what should we store at this location in memory, or that location, or that location. So even though this initializes the variable data, or str in our case, to be a particular location in memory where there is space to store a bunch of integers, we haven't specified what gets stored there yet. We haven't specified the value. And every time we run this, we're going to see different values stored in those memory locations. All right, we are out of time. But that's some stuff to think about. Come back and ask questions on it tomorrow. And then I want to go back and I want to wrap up talking about VI tomorrow. And then we'll go on to something else. So do ODP 411B, ask questions about that, think about this stuff, and I will see you tomorrow.